Okay, so that was an example about a two-tailed test. Now let's talk about a one-tailed test. So suppose that we actually don't really care about whether mu is too large, okay? Because these are packs of candies to be sold to consumers. If consumers get a candy bag that is really heavy, actually they are happy. They will still come to our stores. So at least at the consumer side, that's not a problem. Okay? Obviously at the cost side it's a problem, but let's assume at this moment we think that's fine. So all we want to know is whether we need to fix the problem that there are bags of candies that are systematically too light. Okay, so suppose that we modify the hypothesis into a directional one. We want to know whether mu is too small. If we have evidence showing that mu is too small, shut down the machine and do something. If we have evidence showing that mu is too large, do nothing. Okay? In that case, let's set mu to be less than 1000 in our alternative hypothesis. We still follow our assumption that sigma is set to be 200, n is still 100, and alpha is 5%. So the numbers here are the same. The only difference is that our our alternative hypothesis becomes a one-tail hypothesis. Okay, in particular, left tail hypothesis. So this is a one-tailed test or a left-tailed test. If we have a strong evidence showing that's true, eventually our claim would be that mu is less than 1000. We need to find a distance d such that if 1000 is greater than x bar for a large enough number, then we claim that's true. And we want the probability to be just 5%. Okay, so the only difference is that first, the direction here is input into the hypothesis, and the second, the calculation becomes the calculation of a one-tail probability. Okay, so now we want to calculate this. And this is nothing special than just a single software step, right? So we can find that D is 32.9. So technically, please tell yourself how to do this. Okay? And then graphically is that we now say that our rejection region is from negative infinity to 967.1. As long as x bar falls in the region, we should reject H0. And in our example, this is exactly what's happening. X bar is 963, which lies in the rejection region, and then we should reject H0. The deviation from 1000 is large enough, and the evidence is strong enough. In this particular example, 967.1 is the critical value for rejection. If the sample mean is more extreme than, in this case below, more extreme than the critical value, or in this case more below the critical value, we should reject H0. Otherwise, we should not. Okay? And then in this example, we claim that there is a strong evidence showing that mu is less than 1000. So our concluding statement in this case would be, because our sample mean lies in the rejection region, we will reject H0. There is with a 95% confidence level, there is a strong evidence showing that the average weight is less than 1000. We now have a strong evidence to support the alternative hypothesis. We should shut down the machine and do something. Now it's time to compare one-tailed tests with two-tailed tests. Okay, so one thing that as researchers we need to know is when should we use a two-tailed test and when should we use a one-tailed test, right? We use a two-tailed test when we are lack of the direction information. Okay? For example, probably we got some signal about that the population mean has changed, but it's possible that we have no idea about whether it becomes larger or whether it becomes smaller. In that case, we should just use a two-tailed test because we have no idea about whether to test it is too small or whether to test it is too large. If we know or if we believe that the change is most likely or is possible only in one direction, then we should use a one-tailed test. For example, in the candy bag problem, so some people told us that they suspect that mu becomes smaller. And if mu becomes smaller, that's really a problem. We need to do something to fix the problem. So in that case, we suspect mu is too small. And mu is too small is a problem. So we test whether mu is really too small. Then we use a one-tailed test. If that's not the case, if this is just a, for example, regular inspection, maybe every week, at the end of every week, or at the end of every month, we need to test whether mu is still 1000. If that's just a regular test with no information about the direction, we would use a two-tailed test. So having more information, okay, or in this case, knowing the direction of change, very interesting would make the rejection easier, or that means easier to find a strong evidence to show that H0 is wrong. In our example, recall that 967 is our critical value for the one-tailed test. Okay? And 960 is that for our two-tailed test. Okay? The yellow part is 2.5% and the green part is the another 2.5%. So not very surprisingly, it's possible that for our sample mean, it is not strong enough for a two-tailed test, but it is strong enough for a one-tailed test. We use a one-tailed test because we suspect that mu is too small. Okay, so we have that direction of change knowledge. We suspect that mu is too small. With that additional information, it's easier for us to make a final conclusion. Without that information, we are more conservative and we need really a stronger evidence to conclude that this is wrong. Okay, the process is wrong. So that's why with our 963, it's significant in a one-tailed test, but insignificant for a two-tailed test. Okay, summary. So we need to be able to distinguish the following parts. One-tailed and two-tailed tests, they are different. No evidence showing that H0 is false, and having evidence showing that H0 is true, these are different. Okay? Not rejecting H0 and accepting H0, they are different. And finally, using the equation in the null hypothesis or using them in the null hypothesis. Some people would like to do this, but I would suggest you to just stick with the equal sign. Always use just a pure equality. That would make things easier. Okay, thank you.